In example number 2, we're looking at the relationship between water pressure and the flow rate in gallons per minute of water coming out of a hose. If we look at, I want to just go back and look at this data here. Okay, so here's our water pressure and our flow rate. If we do a scatter plot of this data, and actually I think I'm going to go back to this one right here, sorry. If we do a scatter plot of this data, we're going to have water pressure as our x value and flow rate as our y value, and you see something that looks very much like either possibly a logarithmic graph or possibly like a square root graph. And remember that a square root graph is a type of power function in which the exponent is less than 1, because x to the 1/2 would be a square root function. So we'll try logarithmic and we'll try power. So if I do a real quick regression here, logarithmic regression doesn't fit terribly well, so I'm going to delete that one. If I do a power regression, this fits very well, and as a matter of fact it makes a lot of sense too, because if I have it goes through the point 0, 0 because if x is 0, y is 0. Look at that, it's actually really close to a square root function, because this is 0.050128, so very close to a square root function. Anyway, 0, 0 makes sense, because with 0 water pressure you would expect to have a 0 flow rate. If we look at our R value on this, you'll see also that it's a good fit. So inserting a calculator page, checking my R value, you'll see 0.999953, very, very close to a perfect fit. So let's put in these values here. This is a power regression. The equation is y equals 0.89553 times x to the 0.501128, and our R value is 0.999953. Now to linearize the data, I'm going to take the log of both variables. And to save time a little bit, I'm going to go ahead and show you the results of what we're doing here. If I take the log of both sides of this equation, once again, of my power function, I'd have log y equals log of 0.89553 times x to the 0.501128. Take the log of both sides, realize that I'm taking the log of this entire thing here, so I'm going to have to split this up into the log of 0.89553 plus the log of x to the 0.501128. And then I can bring the exponent out front. The log of 0.89553 is negative 0.04792 if you calculate that, and then we have the 0.501128 times log of x. So notice we have this in linear form. Here's the slope, here's the y-intercept, but instead of x and y we're taking log of x and log of y. So if I were to take log of both of these variables, the data is very straight. I'm going to show you this on my calculator here. So there's my original graph between water pressure and flow rate. Here is the linearized graph between log of water pressure and log of flow rate, and notice the equation, there's those same two numbers. When we did a linear regression, there are those same two numbers that popped up before. So when we're doing a linear regression, a power regression, we're really doing a linear regression of the log of both variables. So going back to my notes here. So you can see too, if I do, here's the power regression of the original data, here's my A and my B values, here's my R value. If I do a linear regression of the log of both variables, notice there's my slope and my y-intercept come from taking the log of both sides of this equation, and there's my R value, same R value. So both exponential and power functions can be linearized and therefore have R values. If you look down at this table, this shows you that linear, exponential, power, and logarithmic graphs all have R values. all of them have R values because they can be linearized, written in some sort of linear form. The linear relationship in a linear graph is just R describes, sorry, I'm kind of spitting this out. R describes the strength and direction of the linear relationship between the original two variables, x and y. In an exponential, however, it's describing the linear relationship between x and log y, in a power between log x and log y, and in a logarithmic graph between the natural log of x and y, or log x, but your calculator uses natural log. Quadratic does not have an R value because it cannot be linearized. R squared, however, is considered a good fit if R squared is close to 1. Logistic does not have R or R squared. It's one that is kind of a specialty function that you have to evaluate based on the context of the problem. So this whole concept of linearizing data is going to be, is not something that you have to do an exponential function or a power, or when you're doing power exponential regressions. You don't have to use, you don't have to linearize the data first in order to interpret the R value, but just recognize that the R value is being calculated based on a linearization of the data, and that's why we can use it to see if the data has a good fit.